let's make a start. So last session we were just finishing off looking at getting the Thevenin equivalent for the Laplace domain. Okay, remember we went through and we showed that in the frequency domain we can get from first sort of principles we could get Thevenin equivalent model for the transmission line source. Okay, and in the Laplace domain we can also do the same thing. Okay, because we have these two-port description. Okay, and I'm pretty sure we found VSE, the equivalent source, the equivalent Thevenin equivalent voltage source, and now we just have to find the Thevenin equivalent impedance looking back into this line. Okay, and we need to do that we need to find well, first of all, to get the Thevenin equivalent you've got to remove Thevenin equivalent impedance. You need to remove the independent sources. So we've removed VS from here as a voltage source, so we put it as a short circuit, and we want to look in here at this other side and find the ratio of V2 to I2. Okay, and we know from two-port parameters what the relationship between V2 and I2 is to V1 and I1. Okay, we know on this side, of course, we have this ZS. We have a relationship between V1 and I1. Okay, so we can put that value for I1 into here. Okay, so in this case, we're going to see that I1 equals minus V1 on ZS. Okay, and then we get V2 equals A V1 plus or minus B on ZS V1. Okay, and I2 is going to be CV1 minus D on ZS V1. And so we can find the ratio of V2 to I2. Thanks for telling me, I can't see it. It's going to be A, so these V1s are just going to cancel out, aren't they? It's going to be on ZS on C minus D on ZS. It's going to be A ZS minus B on CZS minus D, right? So, and that's going to give us ZSE, right? Thevenin equivalent impedance. That's when we take, A is from here, so this is A, B, and then C and D. This is minus C, so C is going to be 1 on Z naught S sine, hyperbolic sine of value, and D is going to be minus cos of that value. Okay, so plug them in and you get ZSE. So do that, you get these. So we could create from the two-port model that we've already got of the transmission line in the Laplace domain, we can get this Thevenin equivalent. Okay, is that clear? Pretty straightforward. Okay, and with that Thevenin equivalent, we could solve for all the unknowns. Okay, so we could solve what the currents and the voltages at the load would be. Okay, so we'll look at a couple of special cases. Okay, in particular, if we've got a matched source impedance. Okay, so both in the frequency and the time, the Laplace domain. So if ZS equals Z naught, okay, then we could plug that into our formula sheet to get the Thevenin equivalent. Okay, and we'll find that comes out to be Z naught. Okay, so and we can find, so independent of frequency. Okay, important thing, because this beta depends on the frequency. Beta equals omega square root of LC. So it's independent of frequency, and we can also find this. You can also do that in the Laplace domain, and we can also find VSE as well. Okay, for the case where it's the source impedance equal to Z naught. Okay, so we've got VSE here equals Z naught VS on Z naught cos beta L plus J, and ZS is going to be Z naught. So this is also going to be Z naught sine beta L. So all these Z naughts will cancel out. Okay, and sorry, you can't see that. Tell me. So you can see here that from Euler's identity, this is e to the J beta L, right? Okay, so VSE is just going to be VS e to the minus J beta L, and beta equals omega square root of LC. Okay, and the delay. So if we've got a transmission line of length L, right? Okay, then the actual time delay, say TD, it takes to go down that distance L is going to be L on UP, which is going to equal L square root of LC, right? Because UP equals 1 on the root LC. Okay. So this e to the J minus here, e to the minus J beta L here is going to equal is basically going to be omega. It's going to be e to the minus J omega TD, the time delay. Okay. So and that if you look in the Laplace domain, probably spelled out more clearly, but that's just effectively a time delay. So it's like, so if you look in the Laplace domain, you see you shift the function in time by tau, then it's in the Laplace domain it's f of s e to the minus tau s, right? Okay, so frequency domain s equals j omega. It's a little bit dodgy, but you can see that this is basically just shifting the source by time, which is equal to the delay of the line. Okay, so there's special cases where like you have a matched source impedance. Effectively at the load, what you see is a source with impedance, the same matched impedance Z naught, and it's just delayed by time. Okay, and that's true for the Laplace domain as well. Okay, it's true for the Laplace domain again. It's just the VSE is just this, but delayed by a certain amount of time. Okay, is that clear? So that's an important thing to know, matched termination. So we can also terminate the line in, say we've got a lossless line, then Z0 is equal to some R0, okay, and we're going to put load to be equal to R0, okay, so now we've got matched termination, not matched source, but matched termination, okay. And so what we see here, if we look in, if we applied the formulas, and we looked in, we already did that for the source when we said the source is equal to Z0. We see that, looking in here, we're just going to see R0, okay. So it means that if you terminate a line with its characteristic impedance, a lossless line with R0, you won't see any reflections, okay. You can't tell whether that line goes on for infinity or it's terminated in something, okay, because it always looks exactly the same at all time scales, okay. It looks like R0. So you would have seen that in the lab, okay? So you can't tell if the line is finite length or infinite, okay. So okay, again, this is looking at what I just said, is that you have the segment that we just went through. If you had the segment that has a matched source, okay, then you're just seeing a delay, okay. At the end of the line, what you see is the source voltage, but just shifted by some time delay, okay. Okay, so we've been up to here. We've looked at, we've started understanding mathematically what a transmission line is, and developed models. We've developed two-port models. We did a frequency domain model. We just looked at the match line. So we've had a lot of good analysis that we can solve a lot of stuff in the Laplace and the frequency domain. Now we're going to be starting to look at time domain analysis of transmission line. So someone did ask, just before I start that, about applications and doing examples. We will start doing a few examples now, certainly in the prac class. But coming up is an application of a lot of that theory to printed circuit board traces, okay, where we sort of develop a model for driving signals, digital signals over printed circuit board transmission lines, okay, and looking at all the effects that can occur, and developing from those models that we've the frequency domain and the Laplace two-port models to actually try and get some approximate model of what this system actually is, okay, and get some mathematical expressions on the transfer functions of the voltage at the source to the voltage at the load, because in these systems you want to deliver a nice, you probably have some square wave or some other switching signal at the source, and you want to deliver it without distortion at the load, okay. So you're interested in this transfer function, okay, and we look at how we can get that, okay, and what its form is, and understanding how we can choose these various parameters to get accurate transmission of step functions, square waves from the source to the load, okay, and all the things that can happen can go wrong, okay. So that's something coming up as a good example of how to apply all this theory, okay. But now we'll look at this time domain stuff, okay, back to where we were, okay. So we've got our piece of transmission line, okay, so it goes down like this, and it's terminated by, some, say, resistor R, right, okay, and we've got, we call this x equals x0, and this is x equals 0. So we've got V at x0 equals some value, and we've also got I at x0, okay, and then we know that if we launch a forward wave, and there's a little bit of change in terminology in the notes here, so in this section of the notes we call V1 is equal to the forward travelling wave, V plus, okay, and we call V2 the backward travelling wave. It's just as it probably have been sections of notes cobbled together, and there's a slight change in terminology. Okay, but we know for V1, okay, we know that we've got V1 travelling this direction, and the current associated with it, I1, is equal to V1 on Z0 or R0. Say it's a lossless line, okay, V1 on R0, okay, it's a lost line, so Z0 equals R0, okay, so it's travelling down. It gets to the end here, and we've got this Ix at x0, okay, so we know that the relationship between Vx0 and Ix0, that's determined by this component R, right? Because we know that as soon as we put something on the end of that line, okay, it has a VI relationship, and that the VI relationship at that point is forced to be whatever that component says it's going to be. So we know that Vx0 equals R Ix0, okay, and this wave coming down here, but we know that V1, okay, is equal to R0 I1, okay. So there's an inconsistency here, okay. So this means that Vx0 cannot equal V1, okay, because we're saying there's an inconsistency. Okay, so how do we solve what comes in to solve that inconsistency there? Anyone? What is it? What What do we have to fix this problem? What must exist to fix this problem? Anyone? So we have the backward wave, okay? So the backward wave exists, okay, so that this inconsistency can be fixed. Okay? So, and we can find what the backward wave is going to be. So we've got Vx naught, it has to be V1, V2, okay, whatever that is, okay? And we know we've got I x naught equals I1 plus I2. It's going to be V1, say on R naught, minus V2 on R naught or Z naught, okay? And we can solve those, okay? We can solve those to get a ratio between, and we know that we can solve those to get a ratio between V1 and V2, okay? Because we know that Vx naught is equal to Ix naught times R, okay? So we know that, now we're going to put that, we're going to have V1 on R plus V2 on R. It's going to be equal to Ix naught, and that's going to be equal to V1 on R naught or Z naught minus V2 on R naught, okay? So we'll have R naught V1 plus V2 times R naught equals R1 V1 minus R V1 minus R V2, okay? So we can group those and we'd get V2 outside of R naught plus R equals V1 outside of R minus R naught. Okay, so V2 on V1 equals R naught plus, right? No, it's R naught minus R minus R naught on R naught plus R, right? Okay, that gives us the ratio of the forward wave, or it's R minus Z naught on Z naught plus R. Okay, now that's the ratio of the forward wave, the backward wave to the forward wave. It has to exist because you've that termination on the end. Okay, and we call that, we had this last time, we call that reflection coefficient. Okay, and I think we had that in the frequency domain as well. Okay, we developed that, but that's an important parameter of the line, well, of the system when you start using time domain analysis. So we'll look at that more. Okay, we'll use that quite a lot. Okay, so that goes through talking about all this what I just said. Okay, and we end up with this. Okay, reflection coefficient. Is there any questions on that? Okay, so we're going to see eventually get multiple reflections coming back and forth down lines, and you'll need to solve it for this stuff. Okay, so initially, we assume that, and I think pretty much all of our analysis so far, we assume that initially we have no current or voltage on the line. Okay, for zero, and that allows us to use superposition. Okay, so initially we say a source will launch primary wave at x equals 0 on the line, okay, and this is the the forward traveling wave down the line, okay. So after time t, which is given by the length of the line divided by the speed of propagation, okay, it reaches the end of the line, okay, and a fraction of that energy in that that waveform gets reflected back, okay, as a backward wave, okay, and then that reflected wave becomes a new primary wave that travels towards the source, okay, and when it reaches the source, it sees the other end is determined by an impedance, okay. What's that impedance at the source end? Source impedance, right? Okay, so it sees effectively, you remove the actual source by putting a short circuit to voltage, or open circuit if it's a current source, and then the source impedance in, and that's what that backward traveling wave is going to see. Okay? And so it could be reflected again if like either the source, or if both the source and the load are not matched to the line, then you get infinite number of reflections back and forth. Okay, eventually when there's loss in the line, it'll eventually settle down, right? But there'll be infinite number of reflections. So these things repeat indefinitely. Okay. So initially, when you launch something, for that instant that you launch it, you would have seen this in the lab. You launch it, you see an impedance of value R naught or Z naught. Okay, if it's a lossless line, then Z naught is purely real, which equals R naught, right? Okay, and why does it just see that then for that short time? Why? Anyone? It's because the wave hasn't had time to reach the end and come back again. Okay, so initially we just see the line just looks like an impedance of, if it's lossless, it would be R naught. Okay, that's the property of the forward wave. Okay, so we can use that. So we've got to find out. The first thing we have to find out, if we've got a source and it has a source impedance, and then we need to find out what is the actual value of the wave that's launched on the line. Okay, and if we know that the line initially looks like this R naught, of course we have that the voltage relationship between the forward wave and I is determined by that characteristic impedance, and for the time that it takes for it to go down the line and come back, it doesn't see anything else. Okay, then we can use that to find out from this circuit what the actual launch wave is going to be. Okay, so we can just use KVL around there. Okay, and it's just going to be potential divider. Okay, because you can just replace this bit of line for that instance at the beginning, just looks like characteristic impedance. Okay, in this case it's R naught. Okay, so the actual launched wave here is going to be R naught on R naught plus RS. Okay, sorry, here we are. Launch waves here, R naught and R naught plus RS times V of S. Okay, that's what's initially going to be launched down the line. Okay, so if we're looking at, I think this is V of X equals 0. So this is V of S. So V of S is initially a a step from 0 to the voltage Vp, okay, then we can find this is a V of x equals 0, okay, this voltage that's launched down line, or the voltage at this point, okay, is just going to consist of the voltage launched down line, because we said initially that the line is discharged, and that value is going to be R0 divided by R0 plus Rs times Vp, right? That's pretty clear. So how long will that stay like that? That's right. So it's going to be 2 times the length of the line, okay, or the delay in the line, okay, because it has to go there, has to come back, and then something else is going to happen, okay, and that's what we've got to solve, okay. So the first part is to find out what we're going to shove down the line in the beginning, and then we've got to think about what's coming back and going where, okay. So, and to do that, we use these things called lattice diagrams, which you're going to have to use in, 100% you're going to get this in the test, right? So make sure you get them in quizzes, maybe in quizzes, but you'll get it in the prac class, and you'll definitely get it in the test. It's easy for me to make questions like this, okay. Okay, so the lattice diagram looks something like this, where we have one line here that represents what's happening at x equals 0, and we have another line here that represents what's happening at x equals x0, which is the end of the line, perhaps in this case, okay, and we have these t, the time going in this direction for both of these points in the line, okay. So initially everything's discharged, right? So everything's 0, okay, and we want to find the voltages at these 2 points, okay. So initially we know at t equals 0, we initially launch initial wave, okay, and then that we put a line in here that represents that forward propagating wave, okay. So this is going in space and it's going in time, okay, and then that gets to the end of the line in this case at x equals x0, okay. At that end we initially said it's discharged, right? So the initial condition at the end of the line is 0 volts, right? Then we have the incident wave coming in, okay, and that will be whatever's launched at time t, because that's what it's taken, how long it's taken to get down the line, okay. So say we've got a step function, okay. Then we'll have the launch step appearing at time t, and then we'll also have to add on what the reflected wave is, okay. So at that instant that it hits there, it will generate a reflected wave, and that's going to add to the voltage incident on the end of the line, okay. So these two will add together, okay. So, and that will give the total, okay. So the total at some time t, as a function of time at this particular point, is going to be the incident plus the reflected plus, well, initially it was 0, right? So that was initially 0. Then that's going to come back, okay. So that reflected wave, this rho times v1 t minus t or whatever, is heading back in this direction, okay? So we represent this by an arrow going in the reverse direction, so it's going in space and time, okay. So we get back to the beginning and we're going to do the same sort of process. So we've got initial, so initially we had this one here, right? That's still there, so that forms what the initial condition is, okay. Then we've got the incident that's onto this edge of the line is this one here, this reflected from the end, okay. That's going to be incident there, and then we're also going to get another reflected there. If the source is not matched, we'll get a further reflection, okay. And so we're also going to get a reflected there, and that's going to add together. So what we get here at that time is going to be all these things added up, and then this reflected here is also going to head back down the line, and we're going to have at this point we'll have what we had before, which was all of that, okay. It'll be the initial condition, plus we're going to have this reflected, okay. That's this rho s v1 t, but now because it's been back through the line 3 times, okay, plus whatever is reflected back in this direction from that new incident wave, okay. So and that all add up. So it goes on to infinitum, right? Okay. No, matched means, we talked about that. A matched segment, remember we talked about matched segments, is when either the load or the source or both have an impedance of Z0, okay. And you can see, so there's matched source and this is matched load. If we go down, so we can see, so if one of those impedance, so if we've got either a load, if R is either load or source impedance and it's matched, what will be the reflection coefficient? 0, right? So if it's matched, one of them's matched, you get 0 reflection, okay? It's an important thing, okay? So, so in this case, you would see that, if the source was matched, then, you get a reflection here, it would come back, but you wouldn't get any further reflections, it would just stop, okay? If the load was matched, then you just get going from here to there and you wouldn't get any reflection back. So, that's what matched means. Okay, so we can do an example. So we've got Vs, okay, so it's going to be a step function. I think it goes from 0 to 10 volts at t equals 0. This is t, this is V of s, okay. And then we've got it's 100 ohms. Then we've got a piece of line which also has Z0 equals 100 ohms, and it's got t equals, the time delay is t, okay, the time delay, okay. And then we also have another load, the load which is 300 ohms, okay. So first thing we want to find, V of A, and we also want to find V of load, okay. So the first thing we need to find is the reflection coefficients. We're always tackling these problems, we're going to find reflection coefficients, so we know that, and we look at it here, okay. So it's in your formula sheet, okay. So remember that. And if you don't remember it off by heart, you just look in the formula sheet. So it's going to be, so at the destination, we're going to have rho is going to be 300 minus 100 on 300 plus 100 is 200 on 400 equals a half, right? Okay. And here we've got rho equals 100 minus 100 on 100 plus 100 equals 0, okay? So it's matched. So there's going to be no reflections at the source, right? Okay. So then, we can draw our two lines, okay, going down like this. This is T. So we know, so at V of A, so if we've got V of A like this, sorry, how's that? Good, tell me, because I can't see. So no, V of A, what will be the initial voltage it goes to? Someone tell me. So you've got 10 volts here. V of S is going from 0 to 10 volts. What's the initial volt? What will V of A initially be? We're going from 0 to what? This is 100 ohms there. Characteristic impedance is 100 ohms. Half of it, right? So we're going to go to 5 volts, right? Because it's just a voltage divider, okay? And that's going to be going like that for, say up to T until something comes back from the other side, okay? So at least the 2T is going to be stable, okay? Yeah, so we're launching this, 5 volts. It's going down like that, 5 volts, okay? So at this end, after 0, after 1T, we'll see something will be happening, okay? VL, because we'll initially be 0, discharge line, and then we'll see something, okay? So that's going to be, the 5 volts arriving plus what's reflected. And so it's going to be a half times plus a half times 5 equals 2.5. And it's going to give a total of 7.5 volts. So initially it's going to go to a little bit high, 7.5 volts, right? Okay. Now that's going to be heading back down the line like that. So it's 2.5 volts heading back down the line. Now that's going to arrive at 2T, right? So initially we've got, so here we had, initial was 0. Here we've already got 5 volts from before. That's our initial. It's going to have 2.5 volts. And then we could have a reflected wave, but, well, the reflection coefficient is 0. Okay. So we don't get anything going back. Okay. So plus 0 times 2.5 equals 7.5 volts. Okay. So this will go up to 7.5 at 2T. Okay. So this one, okay, so we have 5 volts is launched, okay, it's the forward going wave. It gets to the end of the line. So at time equals T, we see 5 volts suddenly appear. But we also have but because of this mismatch between, Z naught and RL, we get a reflection coefficient. Remember, that causes a backward wave to be formed, okay, to account for this inconsistency. So the reflection coefficient of that backward wave, well, the reflection coefficient is given as a half, okay? So it says a half times 5 is what's going to be reflected back. But that exists. So you've got to remember that at any point, V at a particular point X equals L on the line consists of V1 plus V2, forward and backward waves, okay? Now the voltage and current at a particular point on the line is not just the forward wave, it's forward and backward waves, right? Okay. Sorry. No, it says 7.5 volts. There's 7.5 volts. So as soon as that 5 volt gets there, it creates a backward wave. And so that voltage across that 300 ohm resistor will instantly be 7.5 volts. Is that clear? The backward waves created as soon as forward wave hits the load, okay? And it's sent back. And the two of them so remember that always on the line, it's, the voltage is not just the voltage of the forward wave, but also the backward wave, okay? At the point, okay? This is what you're seeing in this particular case. A good thing, we'll just finish off there. So there's no further reflections because the source in this case, right? And you will get a lot more complex problems in exams or quizzes or in the prac class. You might have multiple lines and multiple reflections, okay? So it can get tricky, okay? The other thing, a good thing to check is what would happen in the steady state. So say if you had this step occurring and, you let everything die down. And if there's loss in the system, like if there's, if the source or the load has some finite resistance, i.e. it's not a short circuit or it's not an infinite open circuit, you always have energy being lost in resistors, okay? So as long as there's some finite resistance in the circuit, then eventually it will die down to the steady state if you just have a step, okay? So just if you have a single step at the beginning. A good thing is to think about what would be, how would you find the steady state response of this circuit, if you just have a single step and you assume everything dies down. What would the transmission line look like in, the very, very low frequencies at DC? Sorry? It would look like a short circuit, right? It's just a bit of wire, okay? So all the transients and everything's died out. It just look like a bit of wire. So a good check, is just to see what would happen if it was just the transmission lines were just a piece of wire, then what would you expect would happen? So we've got 100 ohms and 300 ohms and we've got, 10 volts here, okay, because it goes up to 10 volts. Then you would expect this would just be a voltage divider, which would be 10 times 300 on 300 plus 100 equals 7.5 volts, right? That's what you expect for VL. And also, this is VA, and they should both be the same. And then that's what we've got, okay? So a good check and if you've done the problem correctly is to look at